So we were given Tolstoy's integration metaphor as our EMC project, and basically what this involves is taking Tolstoy's ideals and using quite a complex math technique called integration and trying to link them together.
Okay, so during the 19th century, mathematicians including Cauchy, Riemann and Weierstrass developed the theory of calculus, which included the idea of integration. And around the same time, Tolstoy was working on some of his greatest novels. Leo Tolstoy was a famous Russian novelist and philosopher. He was born in August 1828 and died in November 1910. He was born and raised at Yasnaya Polyana, a family estate located 200 kilometers south of Moscow. Tolstoy was born just after the Napoleonic War had finished in 1815, during which Russia had been invaded in 1812. Being raised in the post-Napoleonic world caused him to have strong feelings against leaders like Napoleon. Therefore, he didn't want to award them with too much importance. So he believed that history should be seen as continuous, meaning that the leaders were actually swept along by history and didn't really have any more impact on events than anyone else. He thought the historians were looking at history the wrong way, but instead of focusing on singular events, they should be looking at the entirety of history as a whole, considering events as far back as the ancient civilizations. Doing this would be the only way to correctly understand events and what caused them.
Okay, I'm going to talk about Riemann's sum, which is basically a way to find the approximation of the area under the curve using upper and lower bounds. Okay, so first off, we can plot a quadratic. For example, f of x is 16 minus x squared, and on GeoGebra. And then you can find the upper and lower bounds. First of all, you type in the upper sum into the input box, like there. You type that sort of thing in, and it splits the area under the curve into rectangles, and you measure the area for each of it. With the rectangles, if there's less, it's less accurate, and then more means more accurate, it gets a better differentiation sort of thing there. And you can do the same with the lower bound, with the lower sum function. The upper bound, the rectangles extend outside the curve, and the lower bound, the rectangles are bound within the curve. Okay, once you've got both of those, you can plot them together like this, like so, and you find the average area of both of them, of both the rectangles from the upper and lower bounds to get the area. Okay.
That gives a very approximate area of the area under the curve. So I'm going to talk about integration, which is a much more definite way of finding a definitive area under a curve. So you take some function, e.g. 2 of x plus 1. It plots something like that. And we're interested in this area, so we're interested in that region there, for example. So you take that function, and you can plot it like so to have its two parallel sides as a and b, and the distance between them as h. We do that because it fits very nicely into the formula for the area of a trapezium. And then we can replot that to put points of a and b at its lower and upper areas, so that we can make a lovely equation for its area that looks something like that. But when you take a to be 0, you can simplify this all down immensely to get b squared plus b, which is your final x value, which when differentiated gets back to your original equation. So this is why integration is occasionally called anti-differentiation, if you're seeing it in textbooks somewhere. And there is a very long proof for why this works for all curves of all powers and everything. But it's tremendously long, and it's called the fundamental theorem of calculus, which you can look up if you so desire. But it means that if you take any series function like this, you can integrate it and you'll get a function that looks like that, which are both very lovely and simple. But to summarize, using integration, you can get a nice description of the curve, or the line in this case, to learn more about it.
Right, so now we know what integration and Riemann's sum is, and we can use it so that with Tolstoy's metaphor and his ideals to work out what he was meaning. So if you have a line with the function being the wills of all humanity and the area underneath the function, you're trying to find it in history. And we're going to put that against time and the amount of wills, which we're not sure how to plot at the moment. If you have each rectangle being the age of a dictator-like leader, for example Napoleon, as Tolstoy didn't particularly like Napoleon since he did the Napoleonic Wars. And then once that's Riemann sum, but he wants to make it more accurate, so history is more accurate. And so you can use integration, and as you can see, Napoleon and all the rectangles disappear. So this is in line with what we think that Tolstoy wants all of history to be continuous, and so it's not relied on dictators for its definition.
So, after thinking about how we can link Riemann's sum and Tolstoy's integration metaphor, we have come to the conclusion that if you have maths and philosophy, your interpretation is completely subjective. Now, there are quite a few problems with our interpretation, just down to the fact that some great leaders or evil dictators have more influence than, say, the average person. It is quite frankly nonsense. And the problem with our interpretation is that we create ununiform widths with the boxes, which you can't really use Riemann's sums to work for. But the main problem, really, is that plotting the amount of wills. I mean, how can you plot wills? If you'd asked me at the start how I would plot wills on a graph, it would probably look something like this. So we thank you for listening, and a special thanks to our academic Fazzy and our mentor Charlotte.